Hi, let's discuss mechanical advantage. So, mechanical advantage is useful in levers and and other simple machines. So, mechanical advantage is suppose you're a human trying to do something and you apply a certain amount of force. Well, that would be your input force from the human. And then if you could amplify that somehow, that would be a good idea. And so that would be your output force on top. And so if you can amplify what you can apply, well, that's good. You can lift heavier objects, or you can, um, you know, do work maybe a little more efficiently. This applies to lots of simple machines like levers and gears, things like cranks, axles, and tires. We'll get there. It applies to pulleys a lot. You can figure out a mechanical advantage for those. Um, things like wedges, ramps, inclined planes, screws, things like that. So all those sort of simple machines, you can compute a mechanical advantage for. So our first example, easiest to analyze here, is going to be a lever. So suppose you're pulling a nail. If you pound a nail into a piece of wood and then try to pull it out with your fingers, you're probably not going to be successful. So let's put a nail into a piece of wood, and then let's try to pry that up with a crowbar. So you go to the garage, you pull out your crowbar, and those crowbars are built with a little end that's got a prong on it, and then they got a long end that you can push down on. So you apply some forces to that to get that nail in. The forces in question are, there's going to be a normal force here. So there's a point where the crowbar comes in contact with the wood, and that's really important. That supplies all the upward force that you want to apply on the nail. So there's a force there, and let's call that the output. So that's F out. You want to lift that nail out. Of course, the human is pulling down here. So this one is the input force there. And this is treated just like our teeter-totter problems. This is basic torque. And what you need for torque, besides the forces, is you also need the distances from that pivot point. So you need the distance from that place where that crowbar touches to the perpendicular distance over here. So that's your input distance there, and then this little bit of distance in here, that's your output distance. So I'll just put the same symbols on them just for clarity there. And then you go and you work your statics. So your torque net is 0, and that's your torque in plus your torque out. And torque is this force in times R in. And then the output force, remember our subtlety there, that one is going, oh, it got the signs backwards. So this one is the -1, right? No, that's counterclockwise. Oh my goodness, my arrow's pointing the wrong way. I love doing this on the fly like this because I always make mistakes. So I want that nail to come out. But in fact, the nail is resisting. I got the head on this arrow backwards. So let's make an arrowhead the other way. So now our forces can balance as well. Ah, that's great. So in fact, the normal force is accommodating all of that stuff. The nail is pushing back on the crowbar. So we've got the F out going that way. So F in, that stuff's going to give us a positive torque, and then this other business will give us the negative torque. So F out times R out over there. Aha! Unexpected little twist in the story. Well, from here it's pretty easy. If we want the mechanical advantage, we want to stack it so that it's output over input. So if I add to both sides of this equation, I get F out R out equals F in R in. So all I did was add this second term to both sides. And then I can divide by F in. So I got F out over F in. And this is equal to R in over R out. And output over input is the mechanical advantage. So we have computed our mechanical advantage for here. And it's a big number. So it's the ratio of the long lever to the short lever distance there. So it's going to be good. So the answer is evident. So that's the mechanical advantage for a lever. Let's move on to an inclined plane. So what is the mechanical advantage for an inclined plane? An inclined plane is a ramp. And the idea is that you want to, instead of lifting some heavy object a height h, you want to roll it up some ramp. So you want to go up the ramp some distance like that, and intuitively, that's going to be easier. So you're kind of lessening the effective gravity of the situation. If you just lift, then your force is mass times the acceleration due to gravity. Let's call that one F out. So that's your goal. If you roll it up the ramp, you're going to need less force. And let's drop a few chapters back and not use torque for this one. Let's just note that the work that you're doing is all gravitational potential energy, and it's just mgh. And the work you're doing as you roll it up there is however much force you can apply times the distance that you roll it. And so I think this equation is pretty good. That's probably what we want. So let's note that we've got an mg right there. So there's an mg, and we just wrote that mg is equal to F out. So let's go F out times h is equal to F in times d. That looks cool. So if we arrange this so that it's output over input again, F out over F in, then that's a D over H. And that's a mechanical advantage right there. So the ratio of forces, output over input, is your mechanical advantage for an inclined plane. Pretty cool. So the longer you can make that D, the better off you are in terms of applying your weak human muscles to the situation. All right, so let's go on. Let me draw another picture real quick. I need a sheet. Now, just move over a little bit. So I'll use we'll draw a picture of a wheel and axle. I wonder if that's how you spell it. Somebody will have to check me. So suppose you had a car. Let's look at the tires on it. So you got a couple of tires going here. You've got some kind of shaft that's running through this arrangement, and it's stiff. It's all connected to the tires with intermolecular forces. And then somewhere in the middle, you got, I don't know what you call it, a gearbox or something. And there's a connection to the engine right there. And if you look at it, it's not very big. It's in radius. It's a pretty small box that's there. And so that radius there, I don't know, let's call it R sub gear, something like that. And then that's bringing power from the engine and turning these tires. And so those tires have a much bigger radius. So we'll call that our tire up there. And then when you look at your mechanical advantage, you realize, wait, this is just kind of a rotary lever here. It's the same formula. So your mechanical advantage is still the kind of inverse ratio of radii, our gear over our tire. Should have done that in blue. Oh wow. So you notice though that this is less than 1. Pardon my left-handedness, which covers up the letters there. So that's interesting. So that means that the engine is delivering high forces, and then those really high forces are kind of diluted by the time they reach the tires where the rubber hits the road. So that's kind of interesting. And also we can note at this point that the human muscles and their levers, their bones, are also generally at a mechanical disadvantage in this sense. So their mechanical advantage number is going to be less than 1, which is kind of opposite why we build a simple machine. But sometimes more complicated machines need to apply high forces so that they can then dilute those forces for actions at a distance. Okay, one more little topic, which is pulleys. So mechanical advantage for pulleys. I'm just going to put the picture up here and point at it. In the first case here, if you just pull on a rope with one pulley, so here's our mechanical advantage, 1, 2, 3, 4 cases here. If you just pull on a rope, the tension in the rope can turn corners, but it's always going to be the same tension. And if you use that to lift a weight, you can do it at mechanical advantage of 1. So you're applying 100 newtons and you're lifting 100 newtons. But pulleys are sneaky, and you can add more pulleys. And what you can do is you can add pulleys and make that travel distance of the rope longer. And in the two pulley setup here, you'll notice you do not have the rope connected to the weight anymore. You have a pulley connected to the weight. And then on the pulley are two ropes. And so if the rope has one tension, in this case 50 newtons, that it gets applied twice to this weight. There's two force tension vectors pointing upward on there, and they're both 50 newtons, so it's 100 newton total. So that's a mechanical advantage of 2. The travel distance increases for whoever's pulling, so you're trading distance for force. You can get more complicated. You can add more pulleys, and you can get mechanical advantages higher. It gets faintly ridiculous if you go for higher and higher mechanical advantages. You get so many pulleys in there that the pulleys crowd each other, but you can actually get fairly decently high mechanical advantages. Let's look at this number 4 case. So you're pulling on this rope with one tension, same rope tension for all these guys. But then if you look down here at this arrangement, you've got two pulleys tethered by some steel bar or something, and then the number of ropes is 4. So your mechanical advantage is 4 to 1, and each rope always carries the same tension, but the distance traveled for the puller, whoever's pulling on this, is much longer. Okay, so that's mechanical advantage for the pulley. What you need to do is count the number of ropes attached to the weight. And so there's 1 rope here, 2 ropes, 3 ropes, 4 ropes, and then it's always 1 to 1, 2 to 1, 3 to 1, 4 to 1 for these examples here.